On your screen, I show some PGAClubTracker.com data concerning golf ball brands used by top PGA pro golfers. You can see that 5 golf ball companies are represented here, namely Titleist, Callaway, Srixon, TaylorMade, and Bridgestone. You can also see that Titleist is the most common golf ball on tour by a long shot, and all of these companies have a few different types or models of golf balls. Like Titleist pros are hitting Pro V1, Pro V1X, Pro V left dot, left dash, and yellow, which are all subtle variations depending if the golfer prefers more or less ball feel, higher or lower launch angle, more or less ball spin, and a few other variables that most of us amateurs would not understand or notice while playing. Welcome back to another episode of Paula Marie Close Ask Dr. Paul. Today we're going to highlight the quantification of elastomer crosslinking in a rubber network. So when your boss talks about crosslink density calculations from swell testing, what do you need to know? I have often said that developing elastomers is more challenging than plastics due to the addition and complexity of the crosslinking system. For sulfur curing, the crosslinking system has initiators and accelerators besides the crosslinker sulfur, as shown on your screen. All these ingredients are in low quantities, and to dial in a particular cure level in an elastomer formulation requires precise ingredient measurements, thorough formulation mixing, and consistent processing to complete the crosslinking reactions and give you the same crosslink density month after month and year after year. With the polyisoprene formulation, you can see that the peroxide concentration is about 1% of the formulation, since the peroxide grade is 40% active. And in the last That's Working Knowledge video, we learned that crosslink density drives properties. The information on your screen shows the derivation of the Flory-Huggins Swelling Equation, which is used when a rubber network imbibes solvent, in which mixing and expansion creates the change in the total free energy of dilution. We use the Flory-Huggins theory of mixing and the Gaussian network theory for expansion, and at equilibrium swelling, we can solve for m sub c, or the molecular weight between crosslinks, and finally get an R value after dividing by the molecular weight of the repeat unit of the rubber. A swell test is used to measure m sub c, in which elastomer parts are swollen to equilibrium in a good solvent, and the solvent uptake is related to m sub c, meaning when there is more swell, we have a higher m sub c. By knowing the sample weights, wet and dry, and using the Flory-Huggins Swelling Equation, you can calculate m sub c, or the molecular weight between crosslinks on average, and the R value. And a higher R value means a looser network, and a lower R value means a tighter network with less swell. It is typical for elastomer R values to be in the range of 50 to 100, and 75 repeat units per crosslink is a common target. Swelling an elastomer will allow transient entanglements to escape the network, yet chemical crosslinks and trapped entanglements contribute to the network's ability to absorb solvent and not dissolve. So let's go through the calculations and have some fun with the numbers on your screen. Starting with an elastomer formulation with known amounts of peroxide, polyisoprene, and total weight, we can convert peroxide weight into moles and into molecules, and do the same for polyisoprene. 1.75 grams of peroxide creates 3.6 times 10 to the 21 molecules of peroxide, and 100 grams of polyisoprene creates 3.6 times 10 to the 21 molecules of polyisoprene. Then, if we know 2 molecules of polyisoprene and 1 molecule of peroxide make one crosslink, as you have seen before, you can review the peroxide crosslinking video of natural rubber as a reminder. You can see on your screen that the division of molecules of polyisoprene to the molecules of peroxide gives the R value of 123. Therefore, the given peroxide amount provides 1 crosslink per 123 repeat units on average. And remember, that is only the chemical crosslinking contribution. In elastomer networks, a 1-to-1 chemical crosslink to trap physical entanglement ratio is common, and their contributions to swell are similar. And if that is the case, the R value is cut in half and would be 61, meaning the chemical crosslinks and permanent physical entanglements create a scenario in which the given elastomer network will swell as if there are 61 repeat units from a combination of crosslinks and entanglements on average. I say on average because peroxide crosslinking is random, not a structured event in which it would know to evenly distribute its crosslinking. So this is theoretical work from a given elastomer formulation, which often follows experimental data nicely with the assumption of equivalent chemical to physical contributions and complete usage of the peroxide crosslinker. And these calculations are fun, right? A second calculation is also straightforward using the same peroxide and polyisoprene starting points, and it is easy to quantify the chemical crosslinks in a 0.1 gram elastomer part. First, calculate the weight fraction of peroxide, then convert it into moles and then molecules of peroxide and number of chemical crosslinks in the 0.1 gram part. The calculations show if 100% of the peroxide is reacted or used up, there are 3.1 times 10 to the 18 chemical crosslinks per part. And if 90% of the peroxide is reacted, there are 2.8 times 10 to the 18 chemical crosslinks per part. Peroxide is a half-life reaction, so it is common to cure with a time and temperature profile that gets almost all of the peroxide reacted. And remember, a 3-minute cycle works often for curing of small rubber parts. Knowing about swell testing and how to calculate crosslink density in elastomer formulations, that's working knowledge. Remember to like, subscribe, turn on notification, and even share if you appreciate the content. You can visit our website to learn more about our upcoming Flexible Polymers course. I'm Paul Nash for Polymer E-Club's Ask Dr. Paul. Thanks for watching.